Hello everybody, I'm Davide and I'm going to briefly present you a work I co-author with Francesco Isaia, Alfonso Capozzoli, Valentina Serra and Marco Perino from the Energy Department of Politecnico di Torino. Concerns on climate change have pushed scientific research to explore solutions for a more efficient usage of renewable resources. In this regard, the electrification of the energy final users poses the problem of the integration of renewable energy resources into the power grid, since their high penetration into the electric system raises concerns on the grid stability. This led Johnson, Rhodes, and Weber in 2020 to conclude that the transition to a grid dominated by non-synchronous energy generation should be handled with care. Residential heating has a significant impact in such a context. Indeed, for EU 28 members, the demand for residential heating and hot water accounts for 79% of the final energy consumed by households and 29% of the total electric energy consumption. The electrification of this sector through the adoption of heat pumps will therefore have a considerable impact that requires an assumption of responsibility. In this regard, storage systems appear to be of great importance as heat pump systems can decouple heat generation from heat demand by making use of thermal inertia in the system. Their optimal use, however, requires well-formulated control strategies. The present work aims at formulating and testing different strategies for the control of storage systems serving a nearly zero energy building equipped with rooftop photovoltaic panels. The energy storage systems are namely a hot water tank and an electric battery. The control strategies here formulated and tested aim at maximizing the exploitation of the locally produced energy and better integrating the system with the public power grid. The latter objective translates into a reduced monetary expense, since demand response has been simulated by supposing strongly differentiated electricity tariffs, which the control system tracks and tries to adapt to. The case study consists of a heat pump serving the heating needs of a prototype building bound to be built in Turin, Italy. The facility is a single-floor non-residential building with 2 study rooms, 1 technical room and a control room. The building has been designed as a nearly zero energy building within the context of the PVZEM project at the Department of Energy of Politecnico di Torino. The building geometry and its thermophysical properties have been modeled in detail on Energy Plus. Occupancy and equipment usage profiles were included in the form of schedule objects. Electricity costs have been divided into 3 tariffs chosen so that the highest cost is found during daytime of working days. As to the technical equipment serving the building, we have a heat pump fed by roof-mounted PV panels. An electric battery allows for the produced energy to be stored, while a connection with the grid makes it possible to acquire energy when the battery is flat and to yield energy when the battery is saturated. The water tank is connected to the heat pump through a primary hydraulic circuit, while a second circuit connects the tank to the HVAC distribution system. Both circuits are served by independently operating pumps. 2 different objectives have been considered for the formulation of the control strategies. One is the maximization of the use of locally generated energy and is quantified by self-consumption and self-sufficiency indexes. Both indexes are ratios that see locally generated and consumed energy at the numerator. At the denominator, self-sufficiency has the building energy demand, while self-consumption has the photovoltaic produced energy. The second control objective is the minimization of the monetary expense, quantified by the gross energy cost of the simulation period. As to the control logics, they operate a choice between 2 working modes for the heat pump. In mode 1, the heat pump only guarantees a minimum set point temperature of 35 degrees inside the thermal storage tank, while in mode 2, the heat pump operates until the TES tank reaches its maximum storing capacity, that is when its internal water temperature reaches the maximum value of 45 degrees. 2 strategies adopted as baselines do not operate any choice but those strictly necessary to maintain the system in working conditions. RBC1 shall have the heat pump operating in mode 1 only, while RBC2 works in mode 2 alone. RBC3 is intended to be energy-oriented, therefore it will switch to mode 2 when the battery state of charge is above 90%. RBC4 is conversely cost-oriented, and it will activate mode 2 when the electricity price is at the lowest tariff level. Mode 1 is the choice for the remaining time for both RBC3 and RBC4. Now, for the purpose of our simulation, a lumped parameter model has been chosen for the dynamics description of the water tank, thus obtaining a 0D first-order ODE based on the first principle of thermodynamics. In detail, the heat provided by the heat pump QHP is computed as a function of the difference between the temperature of the produced hot water and the water entering the heat pump. The heat power yielded to the building will determine the temperature drop between the supply water and the water returning from the HVAC terminals. With these two terms, it is possible to compute the time derivative of the tank water temperature with an energy balance equation. The equation guarantees the mass balance as well. Finally, the equation is solved via the forward Euler method. The battery of choice is a commercially available model that provided the reference values for the sizing parameters. The battery dynamics is described by its state of charge time evolution, modeled with a couple of first-order ODEs in discrete form. The two equations refer to the charging and discharging modes, respectively. As to the heat pump, a constant COP has been assumed as equal to 3. The maximum heating rate is set to 9.2 thermal kilowatts, and the water production temperature is set to 45 degrees. The simulation has been run for 2 winter weeks, starting from February the 14th, in order to have a significant range of variation in boundary conditions. For better graphical clarity, only the first week has been plotted. The top plot shows the building heating demand and the variation in electricity pricing. The two bottom plots show the performance of RBC1 and RBC2. It is easy to note a similarity between the two. More in detail, the heat pump power profile of both cases closely follows qualitatively the heating energy demand, which is the gray line in the upper plot. Indeed, with these two strategies, the water tank merely functioned as a hydraulic separator, with hardly any storing capability being employed and no criteria of convenience being followed. As expected, RBC2 works with a water tank at its highest working temperature and therefore allows for a smoother profile of heat pump usage, thus proving to be a preferable choice. If we look now at RBC3 and RBC4, they show much more varied profiles. Notably, they both allow a time shifting between the heat pump use and the building thermal power demand, which proves a better exploitation of the water tank storing capabilities. More in detail, RBC3 has the heat pump work during the middle of the day when the photovoltaic production is at its peak. Indeed, its purpose is to maximize the use of the available renewable energy. Moreover, the battery state of charge, which is the red line, tends not to reach saturation, which limits the amount of energy yielded to the grid, thus increasing cell consumption. RBC4, on the other hand, shifts most of the operating time of the heat pump to the night hours, when prices are low. However, during daytime, when the heating demand is low and there is a high photovoltaic production, much of the renewable energy has to be yielded to the grid as the battery reaches 100% state of charge. So, just as the qualitative observations, quantitative results prove that the different strategies operated in the expected directions. In particular, RBC3 effectively increases the energy-related key performance indexes with self-sufficiency and self-consumption values higher than both the baselines and RBC4. Conversely, RBC4 significantly outperforms all of the other strategies cost-wise at the expense of self-sufficiency and self-consumption. RBC1 and RBC2 are baselines, prove to be poor choices under all the considered aspects as they merely guarantee working conditions for the system. Despite its simplicity, Rule-based control proves to be a sound and effective method that not only guarantees working conditions for the energy systems, but is as well able to obtain significant performances with specific objectives. It is a well-established control method with widespread literature examples and technical expertise among designers. However, its limitations lie in its lack of prediction capability, in its non-optimal solution, and its difficulty in meeting more than one target at a time. All of this suggests further research effort towards predictive, optimal control strategies such as model predictive control. Finally, our ambition has been to provide a simulation platform and a methodology that might serve future studies, particularly to compare rule-based strategies to predictive control ones. Here a bibliography is available with the references for the aforementioned quotes. I'd like to thank you for your kind attention, and I'd like to thank our host as well. Goodbye.